You know the feeling, right? If you've ever trained a machine learning model, you have definitely felt this. That frustrating, expensive, just endless search for the right hyperparameters. It always feels like we're reinventing the wheel, every single time. But what if there's a better way? What if the real trick isn't just learning, but learning how to learn? That's the really powerful idea we're going to explore together. All right, so let's dive right in. To really get our heads around this, we first have to frame the core problem. I like to think of it as the optimizer's dilemma. I mean, you've been there, right? You get a new data set, a new task, and bam, you're right back at square one, trying to tune a model. It honestly feels like you're just turning dials in the dark, just hoping you stumble on the right combination. It's this universal feeling in machine learning, and it raises a really important question. Why does it have to be this way? Well, the honest answer is we're kind of stuck in a loop. As a community, we run literally millions of experiments, but we treat every single new problem in total isolation. It's almost like we're all suffering from this collective amnesia, completely forgetting all the lessons from the thousands of similar problems we've already solved. And let's be really clear here. This isn't just some interesting academic puzzle. This amnesia, this inefficiency, it has huge real-world consequences. We are talking about thousands upon thousands of dollars in compute, weeks of precious engineering time, all of it burned on a problem we should, by all rights, already know how to solve. That's time and money that could be going into real innovation, not just reinventing the wheel. So, how do we break this expensive, frustrating cycle? Well, the answer is one of those things that seems almost painfully obvious in retrospect. We need to start learning from our collective experience. To really build the intuition here, let's use an analogy. Imagine you're a chef. Someone hands you a basket of new ingredients. What do? You're not going to just start throwing them in a pan randomly, are you? Of course not. You'd go to your cookbook library, find a recipe that uses similar ingredients, and use that as your starting point. That simple idea, that warm start, is exactly the intuition we need to bring into machine learning. Okay, so in our chef analogy, that massive cookbook library, that's what we in the machine learning world call metadata. It's really just the collected wisdom from all of our past experiments. Everything, the data sets we used, the model configurations we tried, and crucially, how well they performed. This metadata is the foundation of our shared knowledge. But that begs the question, right? How do you actually find a similar recipe in a library with thousands of them? You need a system. You need a way to describe your new ingredients so you can search effectively. Well, in machine learning, we solve this with something called metafeatures. And it's a truly brilliant idea. We basically create a unique fingerprint for every data set, a vector of characteristics that lets us actually compare them in a meaningful way. And this is where that fingerprint idea gets really concrete. I mean, metafeatures can be pretty simple things, like the number of classes in your data set or the average length of a sentence. But they can also be way more clever. There's this cool idea called landmarkers, which is basically running a super simple, fast model, like a decision tree, on the dataset. The accuracy of that simple model becomes a feature itself. It's kind of like a quick and dirty way to get a feel for the landscape, to understand the problem's inherent difficulty. Okay, and here's where it all clicks together. It's a simple, elegant process. Step 1, we calculate the fingerprint, the metafeatures of our new task. Step 2, we use that fingerprint to search our cookbook library of metadata for the most similar tasks we've seen before. And then, this is the real magic. We take the best performing configurations, the best recipes from those past tasks and use them as our starting point. Just like that. No more starting from absolute zero. Now, I know what some of you might be thinking at this point. Hold on, this sounds a little too easy, a little too simple. And you know what? You're right to be skeptical. That skepticism leads us directly to a really common and frankly, a very seductive misconception about this whole approach. And it's a totally fair question to ask. Are we really learning anything new here? Or are we just building a giant glorified lookup table, a massive database to just find answers we've already seen? Is this true intelligence, or is it just memorization? So let's look at the two ways to view this. There's the shallow view. Yeah, it's just a lookup table. It memorizes past answers. It's brittle. It'll break the second it sees a truly new task. But there's a much deeper, much more powerful view. In this view, this system isn't memorizing answers. It's learning a strategy for finding answers. It's learning to adapt. The ultimate goal isn't a static library of solutions. It's a dynamic, generalizable system that can tackle problems it has never ever seen before. And that distinction leads us to the real danger here. the thing we actually need to worry about. It's not simple memorization. It's something way more subtle, a concept called meta-overfitting. This is what happens when a model gets so good at solving the specific training tasks that its learning strategy itself fails to generalize. It becomes an expert on the past, but a novice at the future. It has perfectly learned the what, but in the process, it has completely forgotten the how. Okay, so if the goal isn't just memorization, but learning a general strategy, what does that actually look like? What are we even trying to build? This is the part where everything we've been building up to really starts to click into place. There's a line from one of the research papers that I think just nails the core ambition here. The aim is to improve learning by detecting, extracting, and exploiting certain information across tasks. Listen to those verbs: detect, extract, exploit. It's not about finding one single perfect algorithm that rules them all. It's about building a system that gets better at the process of learning itself, the more learning it does. And what's so amazing is that this isn't some flash-in-the-pan, brand-new idea. We are truly standing on the shoulders of giants here. If you go back to the 1980s, researchers were already working on concepts like variable bias management, which is all about learning the relationship between problems and the techniques to solve them. Fast forward to the 2010s, and we get these incredible platforms like OpenML, which are essentially giant public cookbook libraries for the whole community. And today, when you see a large language model perform in-context learning, solving a new task from just a few examples in a prompt, you are literally witnessing the culmination of decades of work on this one powerful central idea. Think about that for a second. From that early work on variable bias, all the way to modern in-context learning, it's all just different expressions of the same fundamental concept. And it is a truly profound one. We can make learning itself a learnable task. We can treat it not as some fixed, static process, but as a skill that can be studied, practiced, and ultimately improved. Okay, so the theory is beautiful, right? But the question is always, does it actually work in the wild? Let's make this concrete. So a fantastic real-world example of this is a framework called XAutoLM, and it does exactly what we've been discussing. It builds something called an experience store, which is really just a fancy name for that cookbook library we talked about, and it uses all that past knowledge to give itself a warm start on new tuning problems. And the results? I mean, they're pretty staggering. The warm start search is dramatically faster. We're talking 3 to 4 times faster than starting from scratch. And what about the final model performance? It's just as good, and in many cases, even a little bit better. So just pause and think about that for a second. You get better models in a fraction of the time for the simple act of not ignoring the past. All right, so after all of that, what are the big takeaways? How can you actually apply this? The goal here isn't just to share cool ideas. It's to give you a new set of mental models that you can start using on your own projects, like tomorrow. Okay, here are 3 things I think you can start doing differently. First, treat every single experiment as data. Your tuning runs aren't just passes or fails. They're valuable metadata for the future. You are actively building your own cookbook library. Second, characterize, don't guess. Before you just dive into tuning, take a minute. Calculate some simple meta features. Get an intuition for what kind of problem you're actually solving. Get a feel for the terrain. And third, and this is probably the biggest one, leverage smart priors. A good warm start, one that's based on similar problems you've seen in the past, is the single most effective way to escape that blind, frustrating search in the dark. So everything we've talked about today has been about learning from the past, from experiments that humans have already run. But it opens up a much bigger question. What's next? What happens when these systems can start designing and running their own experiments autonomously? What happens when an AI can create its own curriculum to learn about the future? That is the question that I believe will define the next decade of artificial intelligence. Thanks so much for joining me on this journey.